In this video series, we will fully hunt down the physics of wave nature and begin hunting other magnificent areas of physics. Wishing everyone good studies. In the previous video, we hunted the equation of motion for simple harmonic oscillation and its solutions in both complex and real space. In this video, we will examine how a vibrating system loses energy due to friction. If a vibrating system is within a medium, friction will be applied to it, causing it to lose energy. In the case of electron vibrations, this energy loss occurs through electromagnetic wave emission, whereas in a mass spring system, energy loss may result from surface friction or fluid friction. The simple system we will examine is the mass spring system. The friction force exerted by the fluid on our mass spring system within a fluid is given by Stokes' law. Let us remember that the net force includes both friction and the restoring force of the spring, which drive the motion. By following the method we used to derive the equation for simple harmonic motion, we will apply Newton's second law. This equation gives the equation of motion for a mass spring system vibrating within a fluid. If other forces act on a vibrating system, the same method can be used to derive a new equation of motion, though the solution methods may differ. To solve this equation of motion, let us once again follow the same approach. Observe the phase space of our system and attempt to find the appropriate function. As can be seen from phase space, our motion gradually diminishes inward. The function that exhibits this behavior is the e to the negative theta function. If we multiply theta by a certain value, we can adjust the rate of this decrease according to the effects on the system. Let us express theta in terms of time and apply this solution to our differential equation to determine the constant C1. Our solution for the equation of motion is as follows. Depending on the values that delta takes, the solution and the system's motion will vary. Delta can take three different signs: positive, 0, and negative. If delta is positive, the solution remains unchanged. In this case, the oscillatory motion is so strongly damped that the oscillation ceases before completing even one full period. Energy is transferred to the surroundings very quickly. This situation is called overdamping. If delta equals 0, we have only one solution because C sub 1 has a single root. In this case, the system does not even have a frequency. The oscillation stops directly. This is the last state in which damping allows oscillation to occur before the oscillation ceases completely. Therefore, this state of the system is called critical damping, where energy dissipates more slowly without oscillations. If delta is negative, our roots contain complex numbers, making our function more familiar. This function is the solution of simple harmonic motion multiplied by the damping parameter. If we compare this solution with that of simple harmonic motion, we can find the equation for the angular frequency of this motion. This is the natural oscillation frequency of our mass spring system within a fluid. The constants A and B represent the initial amplitudes of the oscillation, and if we include the phase constants, our most general solution is this solution represents the damped oscillatory motion, and with this solution, all solutions for a mass spring system oscillating within a fluid have been derived. Damped oscillation is one type of oscillation. Another type of oscillation is forced oscillation. By forcing, we mean that two or more vibrating systems interact with each other, compelling changes in their frequencies and amplitudes, leading to forced oscillations. This phenomenon is called forced oscillation. We will hunt this type later and take the final step towards hunting the nature of waves. Stay with science.